Oh, I think that area is pretty empty. All of you on Zoom. Shall we start? Hi everyone. So welcome back to the afternoon session. Our first speaker is Sanmi Koyejo. He is currently an assistant professor at Stanford University, and also he leads the Stanford Trustworthy AI Research. So Sanmi's work is focused on developing practices and also principles for trustworthy AI research, and he has done applications in healthcare and neuroscience. So I think on Monday he mentioned that we should pay more attention to the measurement sciences. So today we'll hear more from him about traceability, enterprises, in benchmarks.
Thank you. It's a very kind introduction. Also very impressive that I think you did that from memory. Right? Oh, close? Okay. It's fine. Not important. Okay. Okay. So real pleasure to be here. Over the next hour, my plan is to talk a little bit about benchmarks in a narrow, but I hope interesting sense, in a way that I hope will be the beginning of a conversation, maybe here and other places, about lots of things we can do to engage with benchmarking and evaluation in our field. In this talk, I'll mostly talk about this narrow question of predictability, which is this idea of to what extent can we, if we measure some performance of a model a certain size or a certain set of parameters, so we vary hyperparameters of a model, to what extent can we infer how the model will behave when we vary size, data size, optimization, tokens, all that fun stuff. So this is something that the field has gotten quite excited about. The simple version of these is called scaling laws. We'll talk about that a little bit today. It gets much more interesting, as many of you might know, once you go beyond sort of log likelihood evaluation to asking what models do when applied to various kinds of downstream tasks. And so the question today would be mostly framed around an observation that while standard log likelihood prediction error seems to have very strong, easy to digest, easy to understand patterns, downstream evaluation of various kinds seems to break. And I'll posit some early work we're doing trying to understand at least some of the angles or uncover some mechanisms by which this might be happening. And I'll frame this around maybe a call to think about measurement metrics as a way to maybe address some of these issues. Okay, so to motivate the talk, I maybe don't need to this audience, particularly given this week, but also just this audience generally, lots of interest in thinking about what happens as I scale up models in various ways. I'm showing early blog posts out of Google when PaLM was a thing, and we thought 540 billion was big. But the argument here was, again, make the models bigger, get a bunch more capabilities out of the models. This is interesting. This led, or I think was correlated with, work asking questions about things like emergent abilities. This has been discussed a few times over the course of this workshop. I'll engage a bit with that in a few minutes. To maybe the 60 Minutes interview that some of you might have seen as another example, where there's this argument that the model somehow taught itself to speak some languages that it never saw. Unfortunately, this particular example is a bit unfortunate, as many of you might know. It turned out that the model did see those languages, just didn't filter enough up the chain to the CEO of Google or Alphabet to sort of know not to say this. But anyways, this idea, I think, has been in the field, something that many people find exciting, this idea that sort of models get big, seem to be able to do lots of cool stuff. I think a particular angle that I find interesting on this question is that I'd argue that more and more, I mean, for sure, a lot of the scaling bet was a big part of like resource allocation decision-making within the field. So this question of, should I pour $1 billion into training a larger model was partially tied to a strong hypothesis about the idea that scaling would actually lead to some meaningful outcomes. I'd argue now more and more, lots of governance, policymaking, public interest, like lots of folks who are now much more aware about AI and thinking about where it might fit socially, often anchor a little bit on what we say we're doing, which is sort of measurement of capabilities of models as part of decision-making processes. So they think more and more about, like when we tell them, the model has some score that ties to maybe reasoning or understanding or whatever framing we use. This seems to have an impact in many places in terms of how they reason through, say, whether a model is ready to be deployed or what uses we can use, or where we can use the models, a bunch of these other questions that are much more downstream. So I'd argue that sort of benchmarks are having an increasing impact on our field, not just within it, which is typically where most of benchmark work was interesting, was again within the field, helping us understand how to iterate through problems, giving us maybe shared tasks that many people could work on. I think more and more so, benchmarks are having this external effect now, which is outside the field, as sort of parts of decision-making and governance of AI tools writ large. So as everyone likes to say, this is my version of if you want to fall asleep, here's the key takeaway. The main thesis of the talk today would be an argument for why and how metrics, which are part of the evaluation process, but not the whole thing, can play a crucial role in predictability of language model performance with respect to scale broadly defined. And I'll mostly talk through a couple of papers. The first one talking about metric choices that are can be discontinuous with respect to the probability of error in a model, and how this can have a systematic and in some cases predictable, I worry about using that word, but we can say ahead of time some effects that we expect to see when we use discontinuous metrics, or metrics that don't allow for partial credit. And I'll explain some of these phenomena. I'll use this as an argument to say, if we care about predictability, which I'll argue is a useful thing, maybe this may be the more speculative part of the presentation, then setting up our measurement processes such that we have much more predictable outcomes as a goal itself seems meaningful. It's tied to generalization. I should tie it to the whole workshop. Maybe less in the sort of standard narrow sense that we think of generalization. This is sort of much less on a particular data set out of sample. This is as I manipulate a bunch of variables around my AI model, things like data set size, model size, length of training, all these things. Can I say something about, so can I essentially predict how well the model will work as I manipulate all these other aspects of training AI models? Okay, that's the main story. Benchmarks are somewhat well-defined within the field, though I think, again, we're sort of better understanding how to taxonomize things and give clean framings. But for the purposes of this conversation, I'll talk about a benchmark as this combination of a data set, maybe multiple data sets sometimes, some notion of metric, if it's multiple data sets, sometimes multiple metrics, which are, again, some sort of scoring function that generally will check how some AI model does as measured by, or respect to some typically ground truth data set as measured by the metric. And then there's a bunch of fuzzy stuff that's really hard to state super formally that I just think about as norms, is like standard practice within the field that we've anchored on as ways that we think we should be doing measurements. So I think there's a lot to do there as well, but again, this is maybe a definition of what a benchmark is. And there's lots of it, as I'm showing here, mostly examples in language, as again, this is sort of a lot of what we're paying a lot of attention to, and this is what this talk is about. But the benchmarks all over the field, they've had this, again, effect of giving us shared goals that we can all work through. I like to tell my colleagues that there's some sort of really cool names. I tell my kids, we sometimes do cool stuff. Hella Swag, I think, is a great name for a benchmark. Other ones, maybe not as coolly named. But anyways, benchmarks with lots of interesting names. There's a bunch of conversation that could be had about exactly how the benchmarks are constructed, what they claim to be measuring, whether those claims are true. I think this is a fascinating conversation for maybe a coffee break or some other time. I won't go into that. A paper that I think does a good job of engaging with some of these questions, particularly questions of construct validity. So these are the idea of developing a benchmark, targeting some conceptual idea, some framing of a problem, and then this gap between, does the benchmark actually measure the thing that we want it to measure? So in measurement science, it's often called construct validity. I think this paper in 2021 from Raji et al. Does a good job engaging a bit with some gaps in our field in thinking about construct validity. But I won't talk about that much. I do think it's interesting and important, which is why I'm mentioning it here. I'm mostly, again, focused on the narrow slice of benchmarks and this sort of evaluation question. From early beginnings and specific benchmarks asking questions about typically single data sets, we now have much richer notions of benchmarks. So Helm, I think, is a canonical example. Benchmarks that, again, so Helm is literally holistic evaluation of language models. So this idea that we can sort of holistically evaluate models. Typically, we'll combine lots of different data sets, maybe lots of different metrics, lots of different ways of thinking about how to prompt models, how to do the evaluation process. So the norm part sort of allow some flexibility there. So again, in some ways, this part of the field has become a bit more mature. I like to mention, this is self-serving, but I'll mention it anyway, with a bunch of colleagues, we did a benchmark in this list of benchmarks. Maybe one thing I'll mention that we think is interesting here is at the time, and I'd argue even now, there's much less focus on benchmarks tied to trustworthiness and safety broadly defined. So I'd say our unique contribution here was attempted to think through what some of these questions look like when focusing on trustworthiness and safety kinds of questions, things like fairness, toxicity, stereotype bias, these other kinds of questions. And I'll leave you to look at the paper. There's also a website, decodingtrust.com, I'm pretty sure, that has more detail, is on Hugging Face, you can take a look. And it's part of now a commercial product out of Virtue AI. But I think potentially interesting. I would also mention this won a Best Paper Award at NeurIPS on the data sets and benchmarks. So some recognition from the community on starting to think about other aspects of evaluation models beyond just the performance questions. So things like, again, trustworthiness, safety, parts of benchmarking. Okay, so one key idea is scaling. So again, I'm guessing not new to this group, and probably you've heard this many, many times today, but over the course of everywhere. It took me a little bit of time to make peace with calling it scaling laws. I don't know how many of you had the same feeling, because I always thought of law in a very formal scientific sense. I've been told that you can interpret law. I'd credit my students from having a sort of broader view than me, thinking of laws, things like Moore's law. So patterns that seem to hold pretty reliable. Moore's law is maybe not a great example because I guess we think it's petering out, but it held for a long time. So from that point of view of law, scaling law seems fine. If you're not worried about this, that's fine. But for those of you who worry about like names of things and have hypothesis versus law, it might be worrying. In any case, this is the observation. And I think by now replicated sufficiently that we think of this as pretty solid empirical evidence. I don't think, at least to my knowledge, we don't yet have super clean theoretical framings for this. So I think it's an interesting open question. But empirically, there's a pretty strong sort of set of results replicated over a bunch of different model classes and various other ways that you can manipulate training models, showing that if I increase some parameters like compute, data set size, number of parameters, I see quite predictable improvements. Predictable here meaning if I look at sort of the performance here, performance meaning test loss, so cross entropy, log likelihood of sort of next word or prediction or token prediction, I see very predictable sort of a pattern of the error decreasing, if I manipulate one of these variables. So parameters, data set size, compute. From early work that I think started to think about or see this pattern, many have argued that this was a big part of, again, many of the bets that some of the large companies made to really invest in scale as a way to try to solve some real world problems, which again led to a lot of the excitement now in the field. But this pattern does seem to be pretty solid. So this seems, at least in, I'd argue, enough that we've decided to make a bunch of real world impactful and maybe resource intensive decisions based on it. Okay, so this part is clean. I also like to mention, as again, part of the motivation for thinking about things in this way, so many of you also know the bitter lesson from Rich Sutton, which I think people interpret many different ways. But the first sentence is mostly saying that we've tried to be clever in a bunch of different ways, but the claim here is that general methods that can leverage computation end up apparently being the most effective and by a large margin, and sort of much more effective than trying to do maybe more clever things in maybe design or other aspects of building or designing models. Mostly placing it here to contextualize again, particularly for those who may not be familiar, this anchoring in the field in terms of, say, I can throw a compute at a problem and make a meaningful advance, and exemplified in the scaling law and some of these outcomes. Okay. While I think it's held quite well, there's been a bunch of recent work trying to expand on it and understand the extent to which these patterns, there's sort of additional degrees of freedom to maybe investigate these patterns. So there are interesting questions in terms of data set quality, things like repetitions, showing that you still see clean patterns and remarkably clean patterns, which again is quite perplexing in a field where we're much used to much noisier signals when we sort of look across model scales. But despite this, the main challenge here is that the patterns are no longer these sort of clean log linear kinds of plots. So you see other kinds of trade-offs as I vary other aspects of building models. So the key question today, again, I've sort of repeating stuff hopefully most of you have seen before, but this idea that scaling laws are a thing, models get better as I increase scale, in terms of cross entropy, so test loss. But now, and I'd argue more and more, we don't care that much about test loss. We care about what does the model do when applied to some real world task that I care about. So we think of this real world task, and one of the ways that we measure real world tasks, as I've argued at the beginning, is benchmarks. And so I'm going to talk a bit about what happens when I combine sort of benchmarking as this evaluation process with the scaling idea, and what do we see. So the picture gets a lot more mixed. There's a bunch of work on this. I'm showing some of the work that got my group interested and excited and thinking about this area. So this is work looking at various kinds of, here, a lot of the early work thought a lot about arithmetic kinds of tasks. So addition, multiplication, subtraction, so basic arithmetic, and asked the question, how well do the models work with scale, and got the main observation that as a global pattern, you do see models get better with scale. So again, the sort of key takeaway is still there, but the pattern is a lot less clean in many cases. And in particular, one pattern that the field has found quite interesting is this pattern where it seems like the performance is essentially flat, at least in the scale here, and then seems to suddenly shoot up. And shoot up often at a scale that seems hard to know ahead of time. And this is, I think, what has been quite perplexing and gotten lots of people excited. Again, I'll talk a bit more about this in a second, but refer to the papers maybe in looking at instances where people have found this behavior of, again, improved performance with scale, but now improved performance, now with parts of the behavior being a lot less of a clean pattern. So if you want predictability and sort of you like the clean log linear plots, this is possibly worrying. If you are deeply into safety, for instance, this is worrying because you might worry that the model, I'm mostly stating a point of view, by the way. This is not necessarily my perspective. This is just stating stated argument. The model might get some capability at some size. You don't know what that size would be if you're worried about safety. In terms of models being able to implement something, not being able to know what size a model will get a certain capability is perhaps worrying from a safety point of view. But you can imagine lots of other reasons if you're trying to make decisions on resource allocation, deployment, governance, a whole bunch of stuff. Having the fact that there are patterns that are hard to predict in terms of performance with scale is potentially worrying. Other people have tried to engage with this. There's some work, for instance, asking if you aggregate and sort of cut off the small models, you see patterns that look clean again. We're going to do a lot of pattern matching over the next, sorry. We like nice, clean plot lines. So that would be the main thing. So if you do that, if you do some filtering, you see clean patterns again. Other work has tried to disambiguate certain patterns, a similar argument, but it's saying, again, you have to look beyond some cutoff. So there's some magic cutoff where sort of models start to get good and patterns tend to become predictable. And sort of if you allow that cutoff, you see the main behavior that we're interested in once again. There's interesting work, or work that I find interesting, sort of recent, that kind of engages with this question. Both of these are this year. The second one is at Colm, the new conference. They argue that part of what is missing is that the tasks or the data sets and tasks have changed over the time, and new models have been fine-tuned to be good at a certain kind of benchmark evaluation task. Older models have not. And part of the gap in performance can be explained by sort of not fine-tuning in terms of making the model better with respect to the data per se, but fine-tuning to the task presentation. So if you like, in humans, this would be something like a framing effect. So the way you ask the question changes how people respond. There's an argument that a version of something like this, I'm throwing my hands all over the place in analogies, so forgive me, but some version of analogy that's versions of this might happen in models. And one way to close the gap, in particular, what's interesting on this plot is that, wrong. In this paper, they're looking, I think both papers actually, but in this paper, they explicitly separate, I believe, November 2023 as a cutoff and look at models before and after and show that if you fine tune to the task presentation, you can actually close the gap a bit more and try to tackle or connect this to some of the story in terms of unpredictable performance. We've done a bit of work that I think engages with this with some Google colleagues and a former student now at Google, Baravan. We did some work looking at downstream evaluation for sort of natural translation kinds of tasks. And we looked at potential distribution shift effects with a claim that, again, distribution shift has an effect on, so as a new degree of freedom, in addition to everything else that we're looking at, potentially distribution shifts, which we might have thought, I think on the panel I mentioned, we thought parts of distribution shift were solved. I think I'd argue now that there may be more nuanced, more interesting versions that show up that make performance, again, hard to predict. This is other work also looking at distribution shift here for order formalization, which is this task of trying to get formal language, sort of colloquial language into sort of mathematical formal language to do things like automated proofs, where we measure a notion of alignment, which effectively is, again, a distribution shift argument, showing, again, that sort of distribution shifts can have a big effect on predictability downstream. So maybe as an aside, but maybe interesting. Okay, so I've done a bunch of hopefully setting the stage. I'll now talk about maybe the two main papers that I want to talk about today. So the first one, or both of these papers, trying to think about this question. Scaling laws are a thing. They seem quite stable. They work for cross entropy, so test error in training the models. When we do whatever we do afterwards and then evaluate models and downstream tests, we seem to lose some patterns. So predictability seems to degrade quite meaningfully. Why is this happening? And today, I think this answer is big and complicated and maybe fun for maybe some of you to engage with. Today, I'll mostly talk about one version, or one part, I think, of an answer to this question, which is in this universe of things you can pick, one of the choices you make is the metric, and some metrics make predictability worse, and some metrics make predictability better. And I'll use this as an argument. If you think predictability is a good property of a benchmark, and I'd argue that it is, but I'm happy to sort of back and forth towards the end of the talk, then trying to pick metrics that give more predictable behavior is maybe a good part of a good design decision in sort of constructing benchmarks and constructing evaluation processes. That's maybe one of the key points of the talk today. Okay, so the first paper, this is a paper presented at NeurIPS 2023 again. I had one of the best NeurIPS of, I think, anyone here, because this paper also got a Best Paper Award, which has never happened to me before. This on the main track, I think also was timely, and we're engaging in this question. We also had a cool title, which I credit to Rylan, Our Emergent Abilities of Large Language Models and Mirage. So the main arguments in the paper, I'll talk about one, thinking about metric choice, explaining unpredictability. Unpredictability here thought of as this emergent story, which I'll define in a couple minutes. Okay, so we've heard the term emergence, we've heard emergent abilities. Some of you might be familiar with this idea, but this has come up over the course of the workshop already a few times. There's not a super precise definition as far as I'm aware. I think of the many things we handwave about, this is one of the in that list. So we've handwaved a bit as a committee around this. But some quotes from one of these papers says or describes this as abilities that are not present in smaller scale models, but present in large scale models. And I think most importantly, and a lot of what captured imagination was this framing or this phrase that they cannot be predicted by simply extrapolating performance improvements on smaller scale models. So again, engaging with this question of predictability as a property of various kinds of benchmark processes. And so again, the example here is, performance looks completely flat at some scale, which they argue is hard to know ahead of time. It shoots up. And so the model, from an external sort of manipulation point of view, the model has suddenly gotten better at the task at a scale that we didn't predict ahead of time. And so we looked, go ahead. Here in this, the x-axis is model scale is measured by training flops. Yeah, so scale here I'm using as a catch-all. It's a good question. Earlier, and this will come up again, the patterns seem to not depend too much on at least three things that we scale easily: compute flops, data model size, data set size. Roughly, things seem to have the same pattern. So very good question. I will be sloppy when I say scale. I'll mean any one of those things. And the patterns seem to either hold or break for all those things. Yeah, good question.
Scaling law, I guess, optimal thing. So it's somehow like the relationship is predictable, I guess.
Yeah. Sorry, I got the beginning of your question and I lost the end. So
I guess you can identify these quantities because these models are trained according to like the optimal.
Sure. So many of these models are trained with respect to optimal scaling laws, but I missed the inference of. So you can identify.
I mean, yeah. Then the x-axis, whether it's flops or data size, it's like roughly monotonic.
Sure. Okay. I think that's also true. Though I would say that at least test error scaling laws seem to be stable even when you change the training paradigm to do something else. So I think the overall phenomenon may not be fragile to that, but the point you're making, I think, is true here. Yeah, like there's a clear relationship between different kinds of scale if you use the recipe. That's good. Great point. Thank you. Okay, so in this paper, we looked at, particularly this original, the Way paper, and looked at which metrics seemed to show the emergent phenomenon and which metrics did not. And we found, and maybe luckily for us, this paper was very broad in that they covered lots of different metrics. So a bunch of different data sets, and they also manipulated lots of different ways of measuring performance on those data sets. And we found that the vast majority of settings where you saw this pattern that is now being called emergence was for one of two metrics, which is either multiple choice grade metric. So this gives, it's an accuracy, I guess both of these are accuracy style metrics. So the first one gives a grade of 1 if the highest probability mass in the sort of token prediction sequence is given to the correct option, 0 otherwise. And then in some settings where we're evaluating sort of directly on the strings as opposed to, say, multiple choice kind of evaluation, you might give a score of 1 if the output string exactly matches the target string, 0 otherwise. So in some sense, these are measuring similar things. The first one makes a lot more sense in multiple choice settings, and the second one makes sort of more sense in things that are not necessarily multiple choice, but still scalably evaluatable, things like arithmetic within models. And so I think this, this piqued our interest and led to, I think, one of the key claims in this paper. So it led to a hypothesis that the claim of emergent abilities may not be fundamental behavior in the model, but perhaps might be better explained as metric choice effects by designers of benchmarks. So as a picture, the idea is, again, if I look at cross entropy per token, this has sort of, again, this super clean, nice pattern in terms of predictability with scale. I can convert this into sort of probably the correct token. The way cross entropy works, this is just negative of the other thing, so or exponential of negative of the other thing. So you can transform back and forth very easily. This is a no-up, essentially, but just saying this for interpretation reasons. If you choose a score that's nonlinear, our claim is you'll get this sharp jump at what seems like an unpredictable scale, which you might call emergence. However, if you choose a linear score, you may not see it. Similarly, if you choose a discontinuous score, you may see this emergence property, and if you don't choose, if you choose a continuous score, you may not. So again, sort of pictorial representation of this argument that at least part of the claims of emergence seem sensitive to metric choice, which lots of interpretations from this. We'll engage with this a little bit at the end. But yeah, again, as the main claim. Okay, so in the paper, we argue broadly about at least 3 things from the observations that we think explain emergence, an emergence phenomenon. One being metric choice, as I just outlined. For various reasons, this has been the one that everyone actually talks about the most. And also is actually the main point of my talk today. So I'll also talk about it the most. But I'll also say, for those who might look at this paper offline, that we make a couple of arguments, other arguments that we think actually matter quite a bit in terms of the statistics of the evaluation process. One of them being using too little data for small models. So actually getting like significant undersampling at the low end of the spectrum, which we think underestimates performance at the low end. And also evaluating too few large models, we think also adds a big variance in sort of the larger models' behavior. And we show in some experiments that if you correct one or both of those things, you get a pattern that, again, seems less sharp in the way that people have argued. But here I'll argue mostly, or at least discuss mostly, the part of the argument that focuses on metrics, because that's what I want to talk about today. Okay. So here's an example where we tried to sort of work through this a little bit. So this is looking at GPT-3 instruction tuned on arithmetic tasks. The rows, the top row is accuracy. So did I get the arithmetic, my calculation correct or wrong? I have either 1 digit, 2 digit, 3 digits, all the way multiplication or addition tasks. Vertically, I have a very simple model, which I won't have time to go into, but it's actually kind of trivial, which we posit as an explanation for the behavior you should expect as I scale the models. It's a very simple sort of toy mathematical model, but we find qualitatively it matches experiments quite well. And we also look at real experiments on 2-digit multiplication and 4-digit multiplication. The main takeaway being, if I look at accuracy, so a metric that, again, is rewarding perfect prediction on arithmetic, I get, again, this behavior of sort of flatness, sharp increase at some scale. If I change the metric to something like token at a distance, which allows for partial evaluation, so it counts the number of mistakes that the model makes, normalized, I get much more, again, think about this as predictability in terms of ease of fitting some simple line as an explanation and extrapolation. We get much more interpretable figures, both in 2-digit multiplication and 4-digit addition tests. And we do this for all of the tests that they look at, so you can look at the paper for additional detail. Okay, so this is on the sort of simulation and modeling side. We also did much more sort of experimental evaluation. So again, luckily, the big bench paper, or this evaluation, looked at a bunch of different tasks, metrics, and model families. So we could just essentially subset from this to test some simple hypotheses. So the hypothesis here was if the emergentability claim did not depend on the metric choice, then you don't expect to see any interaction between emergence and the metric. So there's a correlational claim. And as a sort of pseudo-interventional claim, if the abilities are independent of the metric, then if I take the same task and model family and I intervene on the metric, so go from metric A to metric B, where metric A has a certain property and a metric B has a different one, then I shouldn't see a difference in the emergence claim. And so we show some of this in the paper. I'll just briefly go through some of the results. So here, we look at, as I've argued before, which metrics end up showing emergence. So out of the 39 metrics the big bench uses, 35 don't show emergence, only 4 do. And the vast majority of those also are sort of, again, the subsets that look at effectively sort of multiple choice accuracy or variance of it. So these, they're looking at, again, this highest probability on the correct option or exact string match for things like arithmetic kinds of tests. And so, again, we think this is a meaningful signal suggesting that the metric choice might be part of the explanation for the phenomenon. Question? No? Okay. Yes?
Yeah. I don't necessarily know what all these metrics are, but are they all only looking at one best output?
On one best output is what you're asking?
You draw
Yeah.
a single string from the decoder. There are other things you could do that look
Indeed.
at distribution, or even looked at how much you would have to perturb the parameters to get a high reward answer or something.
Yeah, no, that's a great point. So it's worth saying, one, this was early on in, I say early in the field in the sense of, I think our inference practices were much more straightforward. So we hadn't started to do some of the much more additional things. Sorry, I should be clear. So we looked at a previous paper, and a lot of our results are essentially like reanalysis of their results. And so part of our analysis is dependent on sort of what they have available. I'll show some work where we retrain or refit models later in a second. But to your question, though, most of these are either multiple choice or the sort of arithmetic, there's a digit answer. and you're checking correctness of one of those using various kinds of metrics that might either use the probability directly, so something like a Breyer score might do that, or would do sort of some accuracy adjacent thing. So is the answer correct or not, or is the highest probability mass or edit distance or things like that? Yeah. Okay. Cool. Okay. So again, the main claim here being intervening on the metric seems to reveal predictable changes. You go from a sort of model metric, model family metric pair that shows emergence with a certain metric. You intervene on the metric, you don't see that pattern anymore. We think this seems to show some signal in terms of, or at least a key finding with respect to the emergence claim in the paper, yes?
Do you have any sense of what type of metric is predictability?
Yeah, so in the paper, we hypothesize that nonlinearity and discontinuity of the metric with respect to the probability score. So the token probability underneath the model seems to be a good explanation. And so models that use scoring that allows for either sort of smoother with respect to the probability or allows for partial credit seem to not sort of suffer in this way, sort of the main claim in the paper. One maybe tongue-in-cheek thing, but actually people seem to like, I'll defer to the paper, I don't have it here at all, but we looked at an image autoencoder task in a setting where no one had ever thought to claim emergence, which is, I'm just trying to reconstruct an image. And we changed the metric from a standard reconstruction loss, like a squared loss, to an indicator loss that sort of gives you perfect performance if you're beyond some threshold, zero performance if you're less than it, and the curves give you exactly what you'd expect. So you see an emergence curve in autoencoders if you change the metric to something that has a sort of indicator type behavior. So as an example of, again, other places where this can show up. Yes?
Thank you so much. This is so cool. For when we talk about like predictability itself, from my understanding, we have like an intuitive definition of it as like into the graph, like straightforward or not. Is there like an empirical way to measure predictability?
Yeah, that's a good question. So I would think of predictability as measuring that, which is fun because now we have sort of measurement of measurement. But I would think about this as goodness of fit on any curve that we fit on. So maybe one of two ways. So goodness of fit on some curve fit post hoc to performance, and or the ability to predict, which I think is actually the more important signal that we hope to get. So as I think the coolest version I've seen is Tetsu, whose name keeps coming up. But he had this paper recently where they pre-registered some predictions. They did a similar kind of thing on like, to what extent can we predict behavior of models as we scale things up, and they pre-registered their predictions. Have you guys tested your pre-registration yet? Excellent. Okay. So that's, I think, even stronger as a notion of predictability claim. I don't know if you're talking about this, but cooler than this, maybe, to your point. Okay.
Yeah, two questions. So the first one is for the ones that are nonlinear transformations, can you like derive a transformation of the metric that makes it predictable again? Yeah, that's one.
Yeah. Maybe. I don't know. These are functions. They're sort of fungible in a bunch of fun different ways. At a high level, probably yes. Part of what, at the end, I'll touch on this a little bit, is I think predictability is a good like desiderata for thinking about choosing evaluation processes. I also think sort of human interpretability is important, and that's something we're trying to think about. And I wonder a little bit if I, again, try to like unlinearize or linearize something that's nonlinear, it might break some part of that chain. So I don't have a clean answer for you. In principle, purely mathematically, probably yes, as long as it's not lossy. Yeah. In practice, maybe tricky. Or if it's invertible as a trivial claim. Yes.
So we know that in some cases, at least, there is this kind of emergence phenomenon for modular arithmetic in theoretically, even when you measure it with a square law, there is a very clear sort of phase transition from not learning something to learning. It's very sharp. Do you think that there may be different mechanisms? Some of the mechanisms for emergence of this type, and some of the mechanisms may be something else?
Yeah, so almost definitely there are lots of mechanisms. I'll push back a little bit, though mostly offline for time, on things like arithmetic. So I think what we found is if partial credit metrics, which are things like token added distance, are meaningful for, and I'd argue as a sort of meta argument that metrics that allow for partial credit are, I'd argue, much more useful for scientific applications because they give you some signal on like how can I improve as opposed to this sort of yes/no thing. But if you allow for metrics like that, you don't see this complete zero, like this pattern in the exact same way. I'd also say that if I sample better, which is one of the arguments I made earlier, what I see is that even in the low performance part of the curve, it's not zero. And in fact, if you're looking to fit a parametric curve, there is a good parametric curve that fits the thing. And it's actually pretty well explained. I glossed over this, but I think we can take a look offline. So this is a version of this question in arithmetic. It's actually pretty well explained if I just look at a very dumb version of the mathematical model here is actually quite stupid. It says, I'm going to assume that there's no sequential correlation. I'm just going to flip a coin, probably of getting a digit right in a, say, 5-digit sequence. And I'm going to look at sort of the accuracy of getting all 5 digits right. And this is a probability 101 kind of thing you might give in a homework class. And the exact curve you expect to see will look something like this, where the sort of accumulated probability of error across the sequence, even in an independent type setting, will be close to 0. And then at some point, you have enough accumulated probability. It's under the assumption that as models scale up, the probability that it makes an error is increasing with the scale independently. So I'm not modeling the whole thing. I'm just saying, I'm going to treat this as a next token predictor. I'm going to model the probability that's going to make an error in the next token as just some fixed probability number. And I'm going to allow this thing to get bigger as I scale up the model with some parametric curve, say the original scaling law curve, which captures probability of error. And if I ask how well, like essentially, what do I expect in terms of error behavior of a set of predictions if I model each individual prediction? This is the exact curve you get. Again, sort of easy to get out. So if what you think is important is sort of a pattern that's predictable. One argument is if I change my metric, I again get a token error distance, get a predictable pattern. If I keep the same metric, but I sort of account for the fact that this is going to be low probability type events, so I sample more, I also get a pattern that I can I have much more predictable pattern. It's not 0 per se, but sort of small increasing values in a way that we think we understand pretty well for things like arithmetic. Okay, I'm happy to go offline. I mean, it's one of those I can't prove a negative kind of thing. So does there exist some pattern that sort of our hypotheses would completely break on? Probably, but I don't think arithmetic is one of them. I think it's the main argument here. Yeah. Okay. Other questions? Yes.
Sort of related to the question, but not directly a follow-up. Like, what would be kind of an empirical test of whether something is an emergence or not? Like, is a sigmoid a really sharp increase emergent thing?
So it's a good question. And again, it's one of the issues of the field because it's not that well, like the emergence thing is much more colloquial than precise. There are a couple of papers that attempt to define an emergence score. In the original paper, actually, there was a hand-designed emergence score. I forget the details, but like an emergence label, I guess, human emergence label. And there was some emergence detector that looked at sort of rate of change, and if the rate of change changed too quickly, you could sort of mathematize it that way. So to your question, where's the threshold in a quickly increasing curve where you might say emergent or not emergent? I don't know that that's the key question. I would argue that the key question, and a lot of what motivated and animated this part of the work, is whether or not when this is going to shoot up is something that I could predict or not. So in some sense, the fact that it's so it's not that controversial. I would argue uncontroversial for most downstream benchmarks. There are of course some outliers that you expect performance to increase. So that part is clear. The particular pattern varies. I think whether we want to call this emergence or not, again, is kind of fuzzy. The part that I think has seemed to have mattered the most is, can I ahead of time predict when the sharp thing will happen? And the counter argument here is, for arithmetic, if I, again, do better statistics, I can. If I change the metric to something that allows for partial credit or something linear, I get, again, a behavior that I can predict. And so I lose this magic, if you like, is the main sort of counter argument.
So on that theme, I kind of like the magic approach. Can it just, is the jump just to do whatever it's doing better or faster? Or in a situation where you see that jump, also now you see a capability to solve different types of tasks? So like real emergent.
Yeah, and this is a good question, and one I get asked a fair amount. Much more conceptual than theory. I was about to say theory, but I'd see that's premature. But the conceptual framing so far mostly focuses on sort of task by task. I think there's a lot to do, and actually, to this point, Tatsu's paper actually engages in some version of this, like, can I predict across lots of different benchmarks at the same time? So to what extent is there sort of shared, there's some meaningful evidence that, there's strong correlation between lots of benchmarks. They're not that independent. They're probably mostly capturing something very similar. So it's not an answer to your question, but the actual answer is that we don't do this. But there's other work that suggests that you could reason about correlations across benchmarks and think about things that way. Sure. Okay. Yes.
You mentioned on one of your slides that there's 3 potential sources of unpredictability, and then one of them was undersampling of the test set. Could you explain one more time why that creates an underestimate instead of just like a higher variance estimate?
Yeah, I think it's mostly a variance effect.
But the variance effect makes the metric like underestimate the true value.
Most of the two. A lot of the variance effect is mostly on the high end. Okay, so on the low end, the main worry is a sort of signal detection kind of question. So I'm trying to detect something that mostly fails to work sometimes. And so the probability that it works is low. If I'm going to detect something with low probability of error, high probability of error, I need to sample a lot. So that's the main argument there. And the other part of this, the high large model one, is the variance effect argument. Okay, I want to, good, okay. So I have all the paper to cover very quickly. So we did some follow-up work more recently where we narrowed our focus a little bit. I think it's interesting. I want to sort of run by this group, and maybe it again engages with the question via the lens of metrics. Here we focused on multiple choice question answering alone. So we removed, for instance, the arithmetic questions and just asked, when multiple choice question answering breaks, and it seems to break a lot in many benchmarks, do we have some sense of some explanation of where metrics might play a role? So for those of you who are not aware, a lot of our benchmarks use some version of something like this. I ask, I query the model, I give it a bunch of choices, I ask it to pick one of k choices, 3 to 5 most often. And I sort of, this scales well. This allows me to essentially treat this like a multi-class classification problem. And so it shows up a lot. Most I'd argue most benchmarks are actually built in this way. There's some fun issues here, which I'll gloss quickly, but I think also cause problems. So we've done work trying to understand some token bias in multiple choice question answering. The original paper was actually on a completely different thing. We're looking at fairness evaluation, but we ended up being deeply confounded by token bias in a way that was just quite bad. And this led us to read some of the literature, including, I think, some interesting cool work that has just made the arguments sort of exactly that if you're doing multiple choice selection, the ordering of the tokens can make a difference. A bunch of other weird things that we don't fully understand, but that's sort of set as an aside. So here in this paper, we attempted to ask, if we're gonna look at every sample, we'll look at the negative log likelihood of that sample. And then we're going to go through the process of going from the original probability for a sample all the way to some downstream metric. And we're going to look at that process as we vary scale, broadly defined. So all the ways that we've talked about scale. So in pictures, I'm looking at the loss on some benchmark sample. In order to run a multiple choice evaluation, I will first I can go between the probability of a particular token and the sort of cross entropy with this, again, this simple negate and exponentiate process. And then what is done is that you ignore all the tokens outside of the tokens that you actually, the appropriate tokens for the choices. So if it's A, B, C, D, you ignore all the probabilities outside of the probability on A, probability on B, probability on C, probability on D, and then you renormalize. So you mask all the tokens, you normalize to the set of tokens that are sort of in the choice set, and then you pick the one that has the highest one. And then you might evaluate accuracy, yes, no, on the thing that I selected from that set. So standard way that most multiple choice evaluation processes are implemented within language models. So the claim here is that this choice of multiple choice question answering actually has a systematic effect on predictability. So in a bit of math, I think the first math equation in here. So very simple. Again, I look at cross entropy. I can go through the process of how this goes all the way to some accuracy number per sample, and want to understand what happens to the signal patterns as we go through this step. So here's a simple version of what this might look like experimentally. So we have a bunch of different models at, say, different model sizes. Here we actually used mostly size. So log 10 flops in terms of the main inputs of scale. And then you have a bunch of different samples. And for each sample, I measure, if you're going to do accuracy for a single sample, it's just yes, no. So it becomes binary. I'm asking for every model sample pair, did I get the answer right or not in my benchmark? And so I create this large matrix, this large binary matrix of yes, no, correct. But I can do this for a bunch of other metrics. I can do this for instance, Bria score. This will ask the gap between the indicator and the probability that it assigns to that token. And this will give me a sort of real valued number between 0 and 1 that would fill in this matrix. So for any metric, I can evaluate most metrics because we tend to use decomposable metrics. I can evaluate them sample by sample. I can fill out this matrix of model by sample performance. And then I'm going to do a simple correlation because I want to understand how correlated is this behavior. So correlated is sort of this axis to model size across samples. So I can do this across all different samples. And once I do this, there are a few patterns that you might imagine that you might see. So if I look at the correlations, I might see lots of correlations peaked around 1, meaning that the probability, the model size is highly correlated to the performance on the metric on an individual sample basis. I might see -1, which is highly anti-correlated. I might see 0, completely uncorrelated. I might see sort of some mixed spikes in a bunch of different places. We chose to use survival functions to visualize this with the hope that this was more interpretable. Maybe you can tell me after this if this is more or less interpretable. So for a survival function, if I'm highly positively correlated, I expect to see something that looks like a box. If I'm highly negatively correlated, a sort of inverse. If I have a sort of uniform correlation, I'll see sort of flat line and all the patterns in between. Okay, so if you haven't seen this before, popular in statistics. So we did this over a bunch of different model families, details in the paper. And so an example of this is looking at, for instance, the ARC challenge over a bunch of different models. And here are the PDFs of the sort of correlations between the scores of the model and so the PDF of the correlations of the scores of the model with scale. And this is the sort of survival function, again, to interpret roughly how boxy it is telling you how strongly positively correlated the patterns are with respect to scale. And what we're going to try to get at is we want to see, does this high predictability in the original probability score, what happens to that predictability score as I go through the process of running multiple choice evaluations? I'll speed through stuff very quickly. What we show in the paper is if I start with the log probability, I see some amount of high predictability. If I restrict to the correct choice, as I go through the process, so of receiving the correct choice, normalizing, and then looking at the accuracy, I see an explicit degradation of predictability with scale. I'll show this in a couple other ways. So here's the actual correlation value using Spearman correlation. The colors are the steps in my analysis process. So the blue is all the way at the end with accuracy, and the sort of probability that the model spits out is at the beginning. And the main thing, it's not important and all the columns are different benchmarks. And the shapes are different model families. The main takeaway to hopefully get away from this is that as I go through the pre-processing step, I go from something that's roughly high statistic value to things that sort of are moving towards the left. So I'm using predictability as I scale things up. This shows up even more if I use something like the AUC of the survival function. So I see a very strong pattern of predictability getting worse as I go through processing steps. We look at this in scatter plots, so you can show something similar, where I look at the sort of original probability to the probability after I've restricted to the set of choices, and then I go to accuracy and see how predictability changes. I'm glossing through this quickly because I'm about at time. One aside that may be interesting and ties to the earlier comment is that if I use Breyer score instead of accuracy, which is sort of a more continuous score, I see much stronger clear correlation between, say, Breyer score and probability of correct choice than if I do this with accuracy, where the pattern I showed was sort of much more mixed. I think I've lost the slide. Okay, so I'll conclude. So hopefully the main takeaway is clear. Metric choice seems to have a big effect on predictability of performance with scale. And I've showed a couple of papers that try to engage with this. In half a minute, I'll attempt to go through, again, some of this work has been out for a while. We've had a chance to hear from community. The first is the claim that metrics will affect your results is in some ways kind of trivial, maybe. But I think the main point here is if you care about predictability, this is a meaningful choice. I want to think about what effect this choice has. And as I've argued, maybe badly, but I'm also happy to argue offline, that in many scientific and decision-making tasks, actually having sort of partial credit and interpretability in the metric itself is a meaningfully good property that we should actually explicitly be seeking. There's an argument, I think partially expressed here, that most actual metrics people like to use in practice are discontinuous, and so this is maybe the state of the art and sort of the way we should engage in it. A pushback to this is, I'd argue in many cases it's much more convenient than some strong claim of correctness. In particular, things like multiple choice accuracy captures much more ability to solve multiple choice question answering than some real world downstream task like being able to say be useful in a healthcare or law setting. So I think that's a meaningful gap, which weakens some claims about some of the metric choices already made. Finally, there are lots of settings. We've engaged with some of them. I think there's lots of open space here to think about. So metric choice measurement more broadly is something that I've become quite excited about, and a lot of my lab is working on. So if any of this is exciting, interesting to you, happy to have conversations and hopefully follow up offline. go. Okay. I think we're probably at time, but you can tell me.
And then we'll take a 10 minutes break.
What do you think the main applications for, like, I think you mentioned this at the conclusion. What do you think the main applications for, like, the more discrete versus continuous metrics are? Like, how would one decide which is the best for measuring the model?
Yeah. So actually, I realized there are a couple of partial answer to your question. There was a thank you slide, but there's a quote which my student or ex-student now graduated Wale found, which I think maybe speaks a bit to your question, but I think is a meaningful one as we think about, again, the measurement choices in the field. I think metrics are often thought of as sort of a free choice in evaluation design. All of evaluation often, honestly, in our field, but specifically metrics. And I think part of the claim here is that it's not a free choice. It ends up affecting how you interpret the results. And it can have downstream effects. And one of them could be predictability, but there are other, I think, more nuanced, more interesting additional arguments to make. So to your question, where do people like sort of continuous versus discontinuous metrics? I think it's mixed. I think the state of practice is a lot of accuracy evaluation. I think it comes from, I think I've argued here it's mostly convenience. Though there are some real world applications where sort of you need things to be sort of exactly right. I think the gap in getting things exactly right is actually, I'd argue, is way before the metric choice per se. I think like whether the tools are actually up to that task is actually much more of a bigger gap. That said, that's maybe a bunch of places that people care about sort of accuracy style or exact match metrics. I think the field is still figuring itself out. I don't think there's a clean answer to that.
I love that quote.
All right, so let's thank the speakers again. Now we have a 10 minutes break, and then